go, finally. Alright, so we talked a little bit about what is an inverse here. Now, if we're going to find two functions and we want to know if they're inverses of each other, we're going to do a composition of functions, but we have to do it both ways. It has to work both ways. What ends up happening when you have an inverse, when you have one equation and you have the second, the domain of the first one becomes the range of the second one. The range of the first one becomes the domain of the second one because all your x and y switch, right? Your rule over an inverse is a reflection over the y equals x. And this transformation rule says just interchange these values. So the domain from your first one, which had all x's, is now going to become the range of your second one because it's going to have the y's. The range of the first one is now going to change to an x. It's going to become the domain of the second one. That's going to help us a lot when we start looking at these. Now, to prove that they are inverses of each other, and we denote an inverse by this little -1 up here. We do both compositions, f of g of x and g of f of x. God bless you. You can write it this way, you can write it with parentheses. If both of those yield equal x, then we have an inverse situation. Okay. Now, we can still have an inverse situation, you just have to be careful, because sometimes you get something a little bit different with your parabolas, and we'll talk about those. Most of the times, they look really worse than they work out to be. I don't know if you remember them from last year. This looks really bad, but it's not so bad. If we do f of g of x, we're going to take g and we're going to plug it into x. They look bad, but as soon as you plug them in, if they're inverses, they kind of work out nicely. And here's your f. So you're going to take this entire thing and you're going to plug it into this x. Now watch when you do. When you cube a cube root, what happens to it? It goes away. So that's not so bad. So we're going to cube this cube root guy. And don't forget your -1. So when we cube that guy, that goes away. So we're left with this. Now when we multiply this fraction by 2, what happens to the denominator? It cancels out. And our 1's cancel out. So if they're true inverses, they will work itself out nicely. They look horrible, but as soon as you start plugging them in, they work out real nicely. And we also have to do it the second way. We have to do it both ways. So now you're going to take your f and you're going to plug it into your g. You're going to take this entire equation and put it into this x. So you're going to get the cube root of 2x cubed minus 1. Don't forget this plus 1. So what happens to your 1's? Cancel out. What happens to the 2's? Because it's this. They cancel out. So what's the cube root of x cubed? X. So if these are both equal to x, they are true inverses of each other. Another way we can tell is with your graph. If you take these and you graph them, just like they are, and the third graph, you put the y equals x, you'll see the reflection. Sometimes your graph is a little distorted, so do a zoom 5, and I'll show you the difference. It kind of looks a little bit better. Put these guys in. So if we graph this, and in the last one we put y equals x, you'll see your graph. Oops, I gotta change my graph. I know my graph is a little distorted here. I'm gonna do a zoom 5. A zoom square shows you a little bit better. It takes away that distortion a little bit of the rectangle look. See your reflection? Okay. Another way to test this, sometimes it doesn't always look that great. We're pretty sure it's working. If you look at your table and you follow your rule, pick one point, -1, -3. If I interchange that point, what should my second graph have? What point? -3, -1. So -3, -1. And it's in my second graph. Okay, so there's your rule. Interchange your x and your y. So there's a number of ways to look at these graphs. I like putting them on the calculator as well, because they kind of work out nicely. And I don't think today are we doing the calculator? We are. Okay, today we'll do this on the calculator as well. Tomorrow I have a little lab for you guys to kind of work out together. It's kind of a cool little lab with inverses, so it'll kind of tell you if your inverses are working. I like little labs. All right, so if we have a graph and we have to find its inverse, what's the rule? Switch the x and the y. So your rule is interchange x and y, and then solve for y, and then just make this a true inverse. Okay. So you're going to set these guys up and work them out. All right. I write myself notes that I have to tell you, and sometimes I forget to look at them. All right, so we're going to change this guy to a y, make life easy. Did you do this last year? Yeah. Okay. So you're interchanging the x and the y. And you're solving for y. So what should I do? Good. Multiply both sides by 2. Let's get rid of that parenthesis, that denominator out here. So this becomes 2x, and this one's going to go away. Don't multiply the numerator because you took it out of the denominator. Subtract 5. Good. And divide by -3. And then this guy is equal to the inverse notation.
How do you say that?
F to the -1. It's just an inverse notation. Yeah, F to the -1. You can just say inverse notation, that works. Did you guys have to put this in a line format if this was a line? Or do they let you leave it like that? Yeah, I let you leave it like that too. If my grandson is in Pine Bush, he's 11th grade in Pine Bush, and he has to switch this into a line. So he had to take this out and just make it a line. So you realize it's the equation of a line, right? But you're okay to leave it like this. I'm fine with this. Okay. Again, you could put this in your calculator, y1, y2, over the line y equals x. Make sure they're inverses of each other. To prove this, f of g of x, g of f of x. Remember, both have to get done. And what are they going to both equal to? X. Good. This is important that you replace it with your notation. Okay? All right. We just talked a little bit about this before. A function has an inverse, has a true inverse. Everybody has a reflection over the line y equals x. But for it to be an inverse, your original function has to be 1 to 1. How do I check my original function for 1 to 1? It has to pass what? A vertical, and a vertical tells us this is a function, and it has to pass a horizontal test, a horizontal line test. No two elements in the domain correspond to the same elements in the range. If it's a function, it's a one-to-one. So if it's all increasing, decreasing, in other words, this is a cubing function. So your cubing function says it's this. Oh, by the way, I asked Mr. Baker about the arrows. He says that's been around for years, that if it's an asymptote, you don't use an arrow. That's what he read. I still use an arrow. And believe it or not, the Regents want you to still use an arrow, because the Regents takes off if you don't use an arrow. I'm sure we would argue that if there was an asymptote there, but I don't think you have asymptotes in algebra 2. Did you use asymptotes? Not really? Okay. The old algebra 2, no, not really either. If you did, it was just, you didn't really have to label them or anything. Now we spend a lot of time with asymptotes. So this obviously is a one-to-one because it's increasing. It's never going to backtrack and come down is what they're saying. It's not going to turn around like this, so it's never going to fail a horizontal line test. So we know that that's good. How would I find the inverse of this guy? Oh, not why did the third though? I gotta solve for what? Take the cube root. And don't forget just to change this. Now, a cubing one works, but a squaring one doesn't. What happens with the next squared? What does that give you? A parabola. Now, when you take your parabola and you reflect it over this line, it's going to come out this way. Because this doesn't pass a horizontal line test. It's not either always increasing or always decreasing. It decreases, turns, and increases. So it fails a horizontal line test. So this guy doesn't. What we're going to do next week, at the beginning of next week, is we're going to restrict this domain. We're going to say, okay, I still can get an inverse, but if I cut this part off right here, that will give me a true inverse. So on these types of functions, we'll restrict those domains. On a cubing one, you don't have that situation, because it's, don't forget, your domain and your range are all real numbers, and they're interchangeable. Make sense? Okay. And the next little part is just to graph this. Did you guys graph an inverse on your calculators last year? Okay, so we'll do that this time. We're learning all sorts of new things, right? Okay. Sorry. We're big on graphing, sketching. We do a lot of graphing, a lot of sketching here. It's kind of good that way. All right, so let's take a look at first your domain restriction. Do I have any domain restrictions on this? And where would that be? What can this not be? Greater than or equal to? 0. So we're going to add 3, divide by 2. Excuse me. 3 halves to infinity. So let's graph this and just see what we look like. So it looks like a little piece of an arm. This little 3 halves, that's your vertex point, like if you had a vertex point. Okay, that's the point that it's going to start at, where x is 3 halves. Now, to find out what that y is, I can't see it in my table, right? To find out what that y is, do a second calc and put in 3/2. So what's my y? My y is 0, but my calculator didn't exactly look like it was a 0, did it? Because you can't go by your calculator. Your calculator, remember, can't get that exact, especially when it's riding really close to an axis. It won't get that exact. Usually it does better with the x-axis than the y. Sometimes you see a graph and it's this little tiny piece of a curve, but it continues. So always take a look at either your table. In this case, our table's not going to help us that much because it shows us at 2 that we have a 1. 1 is an error, and we know that because we can't use a 1. But we don't get to see the one in between. So test that one in between. Just make sure you test it and you have a good feel for it. So what would the range be for this guy? 0 to infinity. We tested it, we looked at it. Looking at our calculator doesn't always show us that. All right, now, follow these steps with me. You're going to go second program. Program is, I'm going to have to do this because I can't even see this. Here's your program. Second program. And you're going to come down to number 8. Draw inverse. Now we already put your inverse in y1. Second program, come down to number 8. Just scroll down till you hit 8. Draw inverse. We put your, oops, I got 2 of them now. Okay, we put your inverse in y1. So all we have to do is tell it y1. So to get to y1, hit the vars button, scroll over to the y vars, and just hit enter, enter. And there's your y1. Enter your function and press enter now. See your inverse? It just drew your inverse. If it helps you, put your y equals x line over here. And there's my y equals x. It draws an inverse for you. And it should look like the one that we find ourselves, right? However, notice it doesn't give you an equation. It just draws the inverse. It's kind of a good check. So if we were to make the equation for this, how would I make this equation? Switch them first, good. And then you say get rid of the radical by squaring both sides. Add 3 and then divide by 2. So let me try that. Let me put that in there and see if this is working for me. I'm going to put this new equation in here. Oops, not this. Okay, so there's my inverse. Ooh, I did get part of it, but what happened? It made a parabola, because doesn't x squared give me a parabola? So I have to restrict my domain somehow. So I go back to my original domain and my original range. Now watch. We say when we do an inverse, we swap all your x's and y's. So therefore, we have to swap your domain and your range. Your range now is going to become this guy's domain. So this one, we're going to have to restrict the domain from 0 to infinity. Do you see why we had to do that? Okay? Because our equation will look like a parabola, We don't want that other part. Your inverse function is nice. Your draw inverse. Your draw inverse didn't do this part, did it? We did because we didn't restrict our domain. Now, there is a way to restrict your domain. Every year I have to think about how to do it because I always forget how to restrict your domain. If you come over here, you say, I'm not sure if you say comma, let me just try this. X, and then you do math, and you go to second math, you go to test. Oops, sorry about that. My calculator is not always cooperative. Part of it's me. Part of it's me. If you get there faster than me, tell me if it works. I'm pretty sure this is the way you do it. Oops, nope, I said it wrong. It's in here somewhere. It's like this somewhere. Maybe there's no comma. I'll look up to see where this goes. It's pretty cool when you do it. Did you get it? I don't know what happened. I deleted the wrong thing. Maybe you put this in parentheses. Maybe it's this.
I always have to delete the whole thing when I was
Yeah. Yep, there it goes.
Oh, yeah.
I got it. I knew I'd get it eventually. So you can restrict your domain yourself. Just put your function here, your f -1 here, and I put a comma, but that was wrong. It had to have parentheses. To get that inequality out there, it's this. It's second math. It's one of these in the test part. So if you're less than, greater than, take it off that test part. And that usually does the trick. So now look, we match your true inverse. I mean, just something to play with, something to have a little fun with.
Can you go back to what equals so I can write down how you did it?
Absolutely. Maybe I should write that down too, so this time I don't forget. Because after this little unit, I have a little project for you guys. And